In today's lecture, we are going to enter the world of mass spectrometry. You will learn the general types of mass analyzers, the principle and components of quadrupole mass analyzers, time-of-flight mass analyzer, magnetic sector mass analyzer, and ion trap. Mass spectrometry is an analytic method that employs ionization and mass analysis of compound to determine the mass, formula, and structure of the compound being analyzed. A mass analyzer is a component of the mass spectrometer that takes ionized mass and separates them based on mass to charge ratios and outputs them to the detector, where they are detected and later converted to a digital output. There are six general types of mass analyzer that can be used for the separation of ion in mass spectrometry, including the quadrupole mass analyzer, time-of-flight analyzer, magnetic sector mass analyzer, electrostatic sector mass analyzer, ion trap mass analyzer, and ion cyclotron resonance. A quadrupole mass analyzer consists of a set of four conducting rods arranged in parallel with a space in the middle. The opposing pairs of rods are electrically connected to each other. This type of mass analyzer separates ions based on the stability of their flight trajectory through an oscillating electric field in the quadrupole. The field is generated when a radio frequency voltage is applied between one pair of opposing rods within the quadrupole. A DC offset voltage is then applied to the other pair of opposing rods. Only ions of a certain mass to charge ratio will have a stable flight path through the quadrupole in the resulting electric field. All other ions will have unstable trajectories and will not reach the detector. The RF and direct current voltage can be fixed in a way that the quadrupole acts as a mass filter or analyze specific detector for ions of a particular mass to charge ratio. Alternatively, the analyst can scan for a range of mass to charge values by continuously varying the applied voltage. As we mentioned, the electric field in the quadrupole is controlled by the direct current voltage and component U and radio frequency RF voltage V0 cos omega t. Two opposite rods can have a applied potential of U plus V cosine omega t, and the other two rods have the potential of minus U plus V cosine omega t. For a given DC and AC voltages, only ions of a certain mass to charge ratio pass through the quadrupole filter, and all other ions are thrown out of their original path. Accordingly, the mass spectrum can be obtained by monitoring the ions passing through the quadrupole filter by varying the voltage on the rods, which can be achieved by varying the angular frequency omega or the voltage U and V with a fixed UV ratio. In the quadrupole mass analyzer, the x and y motions of an ion can be described by the Matthew equation, where u is either the x or y directional coordinate, x is the redefining of time, E is the charge of the ion, U is the magnitude of the DC potential, omega is the angular frequency of the applied AC waveform. R0 is the distance from the center axis, the z-axis to the surface of any electrode. M is the mass of the ion, and V is the magnitude of the applied AC or radio frequency waveform. By using the reduced term A and Q, the six-parameter equation can be simplified to a two-parameter equation. Thus, when The two opposing forces are balanced. The movement of a charged particle in the electrical field, the particle will pass through the quadrupole and strike the detector. Two opposite rods have the positive potential except for a short period of time when the negative RF voltage exceeds the positive DC voltage. Because of this short period of negative potential, only the lighter positively charged ions will be defocused by these rods. This also means that these rods will focus only on relatively large positively charged ions so that they can be considered as high mass filters. With similar considerations, the other two rods will defocus the positively charged ions most of the time and will focus only on the lighter ion during the short period, while the voltage is positive on these rods. The other pairs of rods works as a low mass filter. By applying the AC and DC voltage to all of the rods, a band filter is created, that is, a filter that allows an ion with a given mass-to-charge ratio to pass through the rods and subsequently to reach the detector. To understand the function of each pair, consider the rods in the XZ plane in isolation. For now, imagine that only an AC potential is applied on the rods. Half the time when the potential was positive, ions would be repelled by the rod charge and would consequently move toward the center of the rods. Likewise, when the potential was negative, ions would accelerate towards the rods in response to an attractive force. During the negative AC potential, an ion comes into contact with the rods. It is neutralized and is removed by the vacuum. The factors that influence whether or not the particle strikes the rods during the negative cycle include the magnitude of the potential, the duration of time the ions are accelerated towards the rods, the mass of the particular ions, the charge of the ion, and its position within the quadrupole. Now imagine that a positive DC potential is applied to the rods in the XZ plane. This positive DC potential alone will focus all of the ions toward the center of the pair of the rods. When the DC and AC potentials are applied at the same time to the pair of rods in the XZ plane, ions of different masses respond differently to the resulting potential. Heavy ions are largely unaffected by the alternating current and as a result respond to the average potential of the rods. This results in heavy ions being focused toward the center of the rods. Light ions, on the other hand, will respond more readily to the alternating AC current. Ions that are sufficiently light will have an unstable trajectory in the XZ plane and will not reach the detector. Only ions heavier than a selected mass will not be filtered out by the XZ electrodes. As a result, XZ plane electrodes only filter light ions and form a high-pass mass filter. Now look at the other pair of rods and the converse of the AC and DC potentials. The rods in the YZ plane have a negative DC voltage and the AC potential is the same magnitude, but the opposite sign as the potential applied to the XZ plane. Heavy ions are still mostly affected by the DC potential, but since it is negative, they strike the electrode and unable to reach the detector. The lighter ions respond to the AC potential and are focused toward the center of the quadrupole. The AC potential can be thought of as correcting the trajectory of the lighter ions, preventing them from striking the electrodes in the YZ plane. These electrical parameters result in the construction of a low-pass mass filter. When both electrodes are combined into the same system, they are able to selectively allow a single mass-to-charge ratio to have a stable trajectory through the quadrupole. Altering the magnitude of the AC and DC potential changes the mass-to-charge ratio that has a stable trajectory, resulting in the construction of mass spectra. Different ions possesses a stable trajectory at different magnitude and reach the detector at different times during a sweep of AC and DC magnitude range. The graph of the combined effect is actually a simplification of the actual stability diagram. One way to generate an actual stability diagram is to perform a series of experiments where a single mass ion is introduced into the quadrupole. The DC and AC voltages are allowed to vary and the stability of the ion is mapped. After performing a great number of experiments, the resulting plot would look like this figure. The shade area under the curve represents values of AC and DC voltages where the ions has a stable trajectory through the potential and will reach the detector. The white space outside the stability diagram indicates AC and DC voltages where the ions would not reach the detector. While any AC and DC voltage that fall inside the stability diagram could be utilized, in practice, quadrupoles keep the ratios of DC to AC potential consistent, while the scan is performed by changing the magnitude of the AC and DC potential. The result of this is illustrated as the mass scan line intersecting the stability diagram. The general stability diagram is illustrated where there is an inverse relationship between the potential and mass. The lighter ions are higher on the mass scan line and the heavier ions are lower on the line. From the general stability diagram, it is also possible to explain how an instrument's resolution can be altered. The resolution is improved when the mass scan line intersects the smallest area at the top of the stability diagram. The resolution can be improved when the slope of the mass line is increased. The resolution will subsequently increase until the line no longer intersects the stability diagram. While it would be best for the line to intersect at the apex of the stability diagram, it is impractical due to fluctuations in the AC and DC voltage. As a result, the line intersects a little below this point, allowing the quadrupole to obtain unit resolution. Once the resolution has been determined, the ratio of the AC to DC potential is left unchanged throughout the scan process. Again, to perform the scan, the magnitude of the AC and DC voltage is altered while their ratio stays constant. This places a different mass to charge inside the stability diagram. For example, if the AC and DC voltage are doubled, the mass to charge ratio of the selected ion would also be doubled. By scanning throughout the voltage range, the quadrupole is able to create the majority of mass spectra produced in today's chemical laboratories. But it should be noted that quadrupole mass filters have an upper limit of approximately 650 AMU. To sum up, Quadrupole mass analyzer is relatively cheap, can be operated in a relatively high pressure, and can easily couple with many ionization methods. The limitations of quadrupole mass analyzer includes a low mass resolution, usually unimass resolution, low mass accuracy, low ion transmittance, and low mass range. The principle of time-of-flight mass analyzer involves the separation of ions based on the time it takes for the ions to travel through a flight tube with a known length and reach the detector. The trajectory of the ion through the TOF mass analyzer depends on its momentum and kinetic energy due to the applied pulse acceleration voltage and mass-to-charge ratio of the ions. Based on classical physics, ions with a lower mass-to-charge ratio will travel the fastest and arrive at the detector first, while the ions with a larger mass-to-charge ratio will travel the slowest and arrive at the detector last. The following calculation describes a TOF analyzer dynamics. The time it takes for the ions to move across the flight tube between the ion source and detector allows us to determine the mass-to-charge ratios. In a TOF spectrum, the recorded peak for any mass-to-charge ratio will correspond to the sum of signals corresponding to multiple and independent ions arriving at the mass detector. The potential energy given to ions in the accelerated regions is converted to the kinetic energy for all ions. Next, we solve the equated equation above for velocity v. Since velocity is equal to the drift path length divided by time, we get t equals to d over v. Then solving for time, we got the following equation using to describe the time in a TOF analyzer. By rearranging the equation above, the expression of mass-to-charge ratio is determined with this formula. We can also describe the mass resolution for ions by differentiating the equation above with respect to mass and time. We got the following relation. Manipulating the equation, we got the following relation used to express the mass resolution. One of the drawbacks of using a linear TOF is poor mass resolution. Factors that cause poor mass resolution include the starting times and locations of ions. The starting times and locations of ions before they are accelerated into the flight tube are different and affect the resolution. In addition, different kinetic energy for ions and the initial orientation of ions also affect mass resolution and give poor results. In summary, the ideal ion source design should form the ions in the same plane, and the generated ions should have the same energy. One approach to improve the resolution of linear TOF is adding a reflectron to the analyzer. There is an applied potential in the reflectron in which reflect ions in the opposite direction to the detector. The ions shown in these diagrams have similar spacing distance before they arrive at the reflectron, and after the reflectron, the ions are further apart. The reason for this is due to the difference in kinetic energy the ions carry. Heavier mass-to-charge ratios ions have more kinetic energy than lighter mass-to-charge ratio ions before and after the reflectron. Therefore, the heavier ions will take longer path and to reach the detector, and the lighter ions will reach the detector the quickest. The difference in time for the ions' flight trajectory is proportional to the mass-to-charge ratio of ions. This figure illustrates the effect of reflectron on improving the mass resolution, where the linear TOF has a resolution of 300 and the reflector TOF has a resolution of 1800. This diagram shows the internal setup of the Agilent 6540 Q12 having a rod pump in the ionization chamber, a single three-stage turbo pump for the quadrupole mass filter and a collision cell, and the other a turbo pump for the TOF analyzer. The ions passing the quadrupole mass filters will be collected and emitted by the ion pulsar, reflected by an ion mirror, and then arriving at the detector. To sum up, the Reflectron Time-of-flight analyzers can provide a high resolution, high accuracy, and high mass range up to mass-to-charge ratio of 10,000. However, it shows low resolutions when being used for the tandem mass analysis. Magnetic or electrostatic sector mass analyzer has horseshoe-shaped glass tube which is evacuated, consists of a sample inlet, electron bombarding source, and accelerating plates on one end and collector slip at the other end. Sample in the vapor form is allowed through inlet and bombarded with electron beam at 70 electrovolt. It knocks off one electron from every molecule, then they become positively charged ion. As these molecules become positively charged, they are accelerated by accelerating plates and travel in straight path. At curvature of tube, there is a provision to apply the electric or magnetic field. By application of electric or magnetic field, they travel in curved paths, and the molecule ions are separated according to their masses and collected. Different fragments fall on a detector, then mass spectrum is recorded. So let's take a look at the configuration of magnetic or electrostatic sector mass analyzer. First, if you turn on the accelerated voltage, then the ions ideally would head uphill and never going to stop. But if we put the curved plate and apply the voltage at the top plate, so that means there are going to be a force applied pushing down. So as the ions moving through the field, they are going to feel the force. The trajectory won't be straight anymore and it will curve down. Let's think about all the force at play here. First, we have a kinetic energy, 1/2 mv squared, that's related to the initial accelerating plate, the v over here. Because the charged ion is moving in the electric or magnetic field, we are going to have a force pushing down on it. Additionally, there's one more force here because the ion is being forced through the curved path. We have a centripetal force as well. So we have a force going up and a force going down. The centripetal force is mv squared over r. According to Newton's law, for the ions that can pass through the curved paths, these two forces are going to be equal to one another, which can be expressed with this equation. By rearranging this formula, we acquire the relationship between mass-to-charge ratio and magnetic field, radius, and accelerated voltage. To achieve better focusing, Energy has to be reduced before ions are allowed to enter the magnetic field. Adopting the principle we explained in the previous slides, we arrive at the single focus analyzers where 180, 90, or 60 degrees can be used. If we coupled one magnetic sector analyzer with one electrostatic sector analyzer, we will have a double focusing analyzer which can provide an even higher resolution. The double focusing analyzer can be used to differentiate the small mass difference of the fragment. To sum up, the double focusing analyzer have very high reproducibility, high resolution, high sensitivity, and high dynamic range. However, it is not suitable for post-ionization methods because we would like to keep low entry energy for better focusing. The double focusing analyzer is also a pricey instrument. As magnetic sector mass analyzer can achieve very high mass resolution, it can be used in accurate mass and isotope ratio measurements. Next, let's talk about the ion trap. Ion trap can store ions and manipulate them in time, consisting of two end caps and one ring electrode. Similar with the quadrupole mass filter, ring electrode comes with an RF voltage and sometimes a DC voltage. In ion trap, the ion enters the area between the electrodes through one of the end caps. After entry, the electric field in the cavity due to the electrodes causing the ion of certain mass to charge ratio to orbit in the space. As the radio frequency voltage increases, heavier mass ion orbits becomes more stabilized and the light mass ions become less stabilized and causing they collides to the wall and eliminating the possibility of traveling to and being detected by the detector. The ion trap usually runs a mass selective ejection where selectively it ejects the trapped ions in order of increasing mass by gradually increasing the applied radio frequency voltage. As ion traps share the same principle with quadrupole mass filter, the ion motion can be described by the Matthew equation where you can calculate the trapping parameters A and Q. The solutions to the equations can be characterized as either bounded or unbounded. Only certain combination of the A and Q that provide bounded or stable solutions as described by the unitless variable beta. If this value is outside a range between 1 and 0, then the ion is deemed to be unstable in the ion trap. The pseudopotential model is a theoretical model used to describe the behavior of ions in an ion trap mass spectrometer. The model is based on the concept of a pseudopotential, which is a mathematical representation of the effective potential experienced by an ion in a trap. The pseudopotential is a function of the position of the ion within the trap and is determined by the strength and distribution of the radio frequency electric field used to confine the ions. For a given RF amplitude, ions of high mass-to-charge ratio will be sitting in shallower potential wells than their lighter counterparts due to their lower Q values. For an ions of a given mass-to-charge ratio, the potential well depth can be increased by raising the RF amplitude. The deeper well pushes the ions closer to the center line of the trap. If the RF amplitude is sufficiently low that an ion resides in a very shallow potential well, it could strike the electrodes and be neutralized. Under such conditions, ions have a similar chance of being lost in either the x or y dimension due to equal well depths. If a higher IF frequency is used and the amplitude is scaled accordingly to keep an ion at the same Q value, ions will reside in deeper potential wells. In other words, higher IF frequency can translate to stronger trapping of ions. The stability diagram is a general representation of the stability of ion in an ion trap mass analyzer. The stability diagram is used to determine the regions of the trap in which ions of different mass-to-charge ratios will be stable, and is an important tool in the design and operation of ion trap mass spectrometers. The stability diagram can be divided into the two main regions, stable and unstable regions. In the stable regions, ions are confined with the trap and oscillate at a constant secular frequency. In the unstable region, ions are not confined within the trap and will be lost or ejected from the trap. The boundary between the stable and unstable region is known as the stability boundary and is determined by the secular frequency of the ions and the strength of the RF field. While the RF field traps ion in the XY direction, it is not effective at confining the ion in the Z dimension. Confinement along the z-axis is accomplished by placing a different DC potential at the end sections of the trap that is higher than the DC component of the center sections. For example, if the four rods of the center sections will all have a DC component of 0 volts, and the positive ion are to be trapped, then the end section must have the positive DC components. This potential difference creates an electric field that prevents the ions that from existing along the trap's long axis. The small DC offset voltage creates a small electric field that pushes the ions towards the center of the trap, including the ions micromotion. This micromotion is superimposed on the secular motion and its frequency is the same as the secular frequency. The motion of ions along each axis of a two-dimensional pure quadrupole field are completely independent and decoupled. Whatever happens to the ion's motion in the x dimension has no effect on its motion in the y direction and vice versa. Ion motion along each axis is rather complex, comprising numerous sinusoidal components in both dimensions. The frequencies of these components are termed secular frequencies, and they are related to the values of beta. Different ions move in the ion traps with their own secular frequency. Since the integer n can range from 0 to infinity, there are a large number of secular frequencies in any given ion's motion. However, generally speaking, the relative strength of each secular frequency drops very quickly from n equals to 0 to 1, 2, etc. The fundamental frequency is the strongest component of a given ion's motion. The term secular frequency is typically used to describe this frequency alone. Since the secular frequency in both the x and y dimensions is a function of beta, ions with different mass-to-charge ratio will possesses different secular frequencies for a given RF amplitude. As the RF amplitude changes, the secular frequencies of all ions in the trap change accordingly. The larger the RF amplitude, the greater the secular frequency. The maximum possible secular frequency that an ion will ever obtain is half of the omega, occurring at the stationary boundary, beta equals to 1. When only RF applied, the ions arrange along the AU axis, heaviest to the left. If the RF amplitude is increased, the ions move to the right along the Q axis. If a small DC offset is applied between the end caps, the ion moves up the AU axis. According to the stability diagram, all the smaller molecules will be ejected if we want to detect a heavier molecule. So the question is, how can we selectively eject a molecule with a certain mass to charge ratio without ejecting all other smaller molecules? The mass selective ejection is a technique used in ion trap to selectively eject and detect ions of a specific mass to charge ratio. This is achieved by applying a voltage pulse to the trapped electrodes, which creates an electric field that pushes ions out of the trap. The voltage pulse is applied at the specific frequency known as the resonant ejection frequency that is dependent on the mass to charge ratio of the ions to be ejected. Ions of other mass to charge ratios will not be affected by the voltage pulse, as their resonant ejection frequency is different. Mass selective ejection is commonly used to obtain high-resolution mass spectra of ions in an ion trap, as it allows for the selective detection of ions of interest while rejecting others. As mass to charge ratio is dependent on the applied RF voltage, the practical limit of RF voltage around 7,500 volts sets the practical mass limit of the ion trap at mass to charge ratio of 650 using the mass selective instability scan. Once an ion is confined with the trap by the RF voltage applied to the rods, in addition to a DC on the end caps, the ion's motion can be excited by applying additional waveforms to the rods. Specifically, a low amplitude sine wave is applied to one rod, while an equal and opposite sine wave is applied to the opposing rod. If the frequency of these waveforms closely matches the secular frequency of a given mass to charge ratio, the ion will begin to resonate with the additional field, moving farther and further from the center of the trap with a linear increase in amplitude with time. All commercial ion traps use some variant of resonance ejection in which they utilize AC waveforms to eject ions from the trap during the mass analysis step. Most commonly, bipolar excitation is performed during a linear ramp of the main trapping voltage as ions move left to right across the stability diagram. Their secular frequency continuously increases. Eventually, their secular frequency approaches the bipolar axis frequency, and the ions begin to resonate, and move further from the trap center. Eventually, the ions have picked up enough energy to eject from the trap together. If done appropriately, resonance ejections can enhance the instrument's mass resolution. There are a few other applications that can be done by using an ion trap, including the broadband isolation and fragmentation. For broadband isolation, it is imperative to first isolate the mass-to-charge ratio of interest when performing mass-mass analysis with an ion trap. All other mass-to-charge ratio values can be ejected from the trap by performing resonance excitations with a range of AC frequency. If done appropriately, a relatively narrow mass-to-charge range can remain in the trap while all others are ejected. Fragmentation. As ions move away from the center of the trap, they pick up kinetic energy. In the event that they subsequently collide with a neutral, there is an elevated amount of energy which can be converted into internal energy. If enough of these collisions occurs, the ions can attain a sufficient internal energy to actually break bonds, resulting in a fragmentation. Such fragmentation can be achieved with resonance excitation by applying just enough amplitude to stretch the ions away from the center of the trap without actually ejecting it out. It is critical for mass-mass analysis, which requires both isolation and fragmentation. Two main problems associated with ion trap are the mass measurement accuracy and the space charge effect. In ion trap, the ions with higher mass require longer time to eject, creating a mass shift. Thus, the internal calibrant is usually required for high-resolution measurement. The other issue is the space charge effect. Imagine that we have ions all positively charged. Ideally, these ions are flowing around in a little box. They don't notice each other's. The only voltage they should be feeling is the voltage applied from end caps. But when the ions get so crowded in there, they will repel against each other and thus distort the applied field. The distorted applied field will reduce the mass resolution as shown in this figure. That's for today. See you in the next lecture. Bye.